Okay, number 3, f of x equals x cubed minus 3x squared plus 3. Find the derivative. Find the second derivative. Find the intervals where it's increasing, where the function is increasing, not the derivative. Find the intervals where the function is decreasing. Use that information to find any x values of relative mins and maxes. Find the intervals of concavity, concave up or concave down. Use the second derivative test to confirm your answers to part D. Use the second derivative to identify the x values of any inflection points. There's a lot going on here. Let's start with the simple one. The derivative of f of x. 3x squared minus 6x. Question B, the second derivative. 6x minus 6. Okay, question C. Identify all intervals from negative infinity to infinity, that's a long way, where the function is increasing or decreasing. How do we set the intervals? How do we decide that it's negative infinity to some x value and some x value maybe to another x value, and then that x value to positive infinity? What do we do to find those x values? Find the zeros of the first derivative. Very good. Same thing you were saying, Mr. Fisher. Find the zeros of the first derivative. So part C, 3x squared minus 6x equals 0. I'm going to factor out a 3x, and I get x minus 2 equals 0. So x equals 0, x equals 0 and 2 are, do you remember what we call those? Critical numbers. Something's going on at x equals 0 and x equals 2. But what we can do now is set up intervals from negative infinity to 0, 0 to 2, and 2 to infinity. We have picked up every number from negative infinity to infinity. And then I take an x value in this interval. Give me a number between negative infinity and 0 that you'd like to evaluate with. Negative 1 would be probably the one I would pick. And if we put negative 1 into the first derivative, what do we get? We get 3, we get 9. Now, based on that, the slope of the tangent line, and this isn't the question, but the slope of the tangent line in this interval is positive. So that means everywhere in this interval, the original function is doing what? Increasing or decreasing? Increasing. If you think about a positive tangent line, the function has to be increasing. Even if the tangent line is getting really flat, the function is still increasing. Give me a number between 0 and 2. How about 1? F prime of 1, what does that equal? Negative 3, which means now that the slope of the tangent line in this interval is negative, which means everywhere in this interval the function is decreasing. Lastly, I'll pick 3. F prime of 3 is going to be 27 minus 18, positive 9. Positive, therefore increasing again. And what we have just done is answered the question in C, identify all intervals from negative infinity to infinity where the function is increasing and decreasing. And showing it just like this is fine. Okay? Increasing, decreasing relates to the slope of the tangent line, first derivative. Okay, part D. Use the information from C to identify x values of any relative mins or maxes. Okay, so something is going on at 0, right? Because from negative infinity to 0, the function is increasing. After 0, the function is decreasing. So that means at x equals 0, the original function has a min or a max at x equals 0. A max. So in D, we'll say a max at x equals 0. What's going on at 2? It's decreasing to 2 and then increasing after 2, which makes x equal to 2 a what? A minimum at x equals 2. Does that logic make sense? Increasing on one side, decreasing on the other, got to be a max. Decreasing on one side, increasing on the other, got to be a min. Part E. Part E. That's funny. That's better than part A. Part E. Identify all intervals from negative infinity to infinity where the function is concave down or concave up. What part of this problem relates to concavity? Original function, first derivative, second derivative. Second derivative. The inflection point, or the point of change in concavity, will occur when the second derivative is set equal to 0. So 6x minus 6 equals 0. So something is going on at x equals 1. Well, not something. Concavity is changing at x equals 1. Concavity, second derivative. So when I set my intervals up, I'm going to go negative infinity to 1 and 1 to infinity. And I'm going to check f double prime of 0. What is f double prime of 0? Negative 6. So does that mean concave down or concave up? Concave down. And here I'm going to use f double prime of 2. That's going to equal positive 6, I do believe. And if it's positive, then concave up. And there's our answer to E. Actually, that's our answer to F. Partially. I don't really like how E and F are written now that I look at that. E says identify all intervals from negative infinity to infinity where the function is concave down and concave up. We did that. Part F says use a second derivative test to confirm your answers to D. Oh, to D. I wasn't reading that closely. To D, the mins and maxes. Okay, so let's look at F. Use the second derivative test to confirm your answers to part D. So part D was about finding relative mins and relative maxes. And our critical points were 0 and 2. Well, you know what? I used both of those as a matter of fact here. So if I plug in f double prime of 0 and I get negative 6, which means it's concave down, and 0 is a critical point, if something is concave down, does that make the critical point a min or a max? Let's think about that. It's concave down. So there's my critical point. So what does it have to be then if it's a critical point in a concave down section? It's got to be a max. So I want to see then, therefore, max. Yes? My instructions just said x values so that we didn't go through that extra step of finding the actual point. That's why I said just find x values. And then if f double prime of 2 is positive 6, that's going to be concave up, which makes this a min. Therefore, min. And then part G, use the second derivative to identify the x values of inflection points. Kind of already did that. That's going to occur when f double prime of x equals 0, and we did that right here. So x equals 1 is the inflection point.